A very good morning to all of you. Welcome to this live interactive session of the NPTEL course Transition Metal Organometallic Chemistry from Principles to Applications. We have had several lectures already aired in this course, and we are approaching the final exam very soon. So it is only relevant that we have this interactive session prior to you going to take up the final exam. So, as is the usual practice, I request you to type in any questions that you may have or queries that you may have uh, in the chat box located on the bottom right corner of your screen, and we will answer them in the order in which we uh, receive. Good morning, Rajat. In case of olefins, where olefin attaches to the metal, the CC bond length increases, so is the stretching frequency decreases, which is similar to carbonyls. Yeah. So, so what is your query? Is that how and why the CC bond length increases? Is that the query? Okay, now if you were to take a look at metal carbonyls as well as metal olefins, the way they bind to the metal center, you'd see that primarily there are two types of interactions uh, uh, which are possible in both the cases. The first and foremost is the forward sigma donation that happens from the bonding olefinic lone pair to the vacant metal d orbital, and from the carbonyl carbon lone pair to the vacant metal d orbital. So these are L-type dative ligand to metal interaction that happens in both the cases, olefinic as well as carbonyl binding to the metal center. Now, over and above, beyond that, secondary interaction, which also happen in some certain cases and or in some conditions, in which field metal uh, orbital donates to the antibonding pi star of the carbonyl. Hmm. So this is metal to ligand back donation. And that happens not only to the olefin where it binds to the pi star ligand of the carbonyl, it also for CO, as well as it also happens to the pi star ligand of the uh, olefin. So this is back donation component. Now, usually the component of back donation is always lesser than that of the forward sigma donation. So because of which primarily both carbonyl and olefin are referred to as L-type, two electron donor ligand. But in certain instances where metal give back to the vacant pi star orbital of carbonyl and olefin, then in those cases, they are good pi acceptor ligands. And as a result, the ramification which sort of comes out, manifestation which comes out of the back bonding is the hybridization of the olefin changes from sp2 to sp3. As a result, what you would see is that olefinic bond getting lengthened. As a result, the pi star getting populated. As a result, the double bond character is lost, and the stretching frequency decreases. These are, but the implication of significant amount of back donation that happens in olefin as well as in carbonyl. So in instances where the back donation is predominant, only in such cases you will see that olefinic carbon has been converted from sp2 to sp3 hybridization, as well as the CC bond order decreasing, as well as the bond stretching decreasing. Yeah. So it is not always that all olefin binding to metal will have this back bonding component. Depends on the metal, depends on how many electrons the metal is having filled in the d orbital, and whether those d orbital are capable enough in terms of the proximity to the olefinic pi star, as well as energy wise they're of the same comparable region to donate onto the pi star ligand of the orbital. So only in certain instances of olefinic binding, you may see significant amount of metal to ligand back donation, and in such cases, you would see that there is this lengthening of CC bond, decreasing of the IR frequency. And as you have rightly said, that this type of bonding is similar to that of carbonyl and olefin. The forward donation is from the ligand to metal is represented by L-type bonding, and the backward donation from the metal to ligand is represented by Z-type bonding. So these are LZ, LZ type of combination, which is seen, sometimes seen, not always seen in case of olefin, as well as sometimes seen in case of carbonyl. Uh, so this is all I have to say about the. Like if any substitution is involved in the olefins, say electron. Yes, obviously. See, there are two components, no? If you have electron donating or there are substituents in the olefinic orbital which will make it electron deficient. So that will sort of influence the metal to give electron to the our olefinic pi star. But that having said, if the metal is, let's say, early transition metal and doesn't have enough d orbital to back donate onto the ligand, so in that case, only having electron withdrawing group on the olefin does not help. So it is a combination of several factors coming together at same point when all of things work out. So ligand should, if the substituents of the ligand which will make olefin more electron deficient, that will certainly point towards or facilitate metal to ligand back bonding. But if the metal does not have enough electron, then obviously metal won't be able to back donate. No. So it is not just only the substituents of the olefin which will trigger the back donation. That is one of the many factors which may influence the back donation. The other factor being the metal having enough sufficient electron in the d orbital to be able to back donate. So that sort of answers the question that you have asked. Do you have any further query on it? So this is a combination of factors. Let's say a donor has to have enough electrons to donate, and the acceptor has to have a vacancy to accept. So it cannot be one-way traffic. Let's say the acceptor is highly electron deficient and waiting for donor to give electron. But if the donor doesn't have electron, then how does it donate? So it doesn't work out. On the other hand, if the metal is a late transition metal, which has a lot of electrons and is already extremely keen on donating, but if the ligand it is binding to does not have a acceptor orbital, then even though the metal wants to donate, there is nothing the ligand can take. So it is a two-way traffic, and they have to meet at the half point of each other. One of the factors will not solely guide it. So as a result, that's why you will see that carbonyl complexes, even alkyne complexes of early transition metals are rare. D0 metals. So do you have any other query? So for people who have joined in late, welcome to this NPTEL uh, uh, live interactive session on advanced transition metal chemistry principles to applications. And in these live sessions, we answer questions uh, 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 which you may have, and we try to answer them in the key in which you text in your queries. So there is another one. Yes, CC activation requires more. So that's very obvious, no? Because the CC is more buried in. They are deep inside. CH, let's say if you look at an alkane or anything, the peripheral bond, the bonds which are on the surfaces will be CH. Whereas the bonds which are in the skeletal bonds would be CC. Now, if you want to break a CC bond, then the metal orbital has to penetrate all the peripheral bonds and then reach the metal CC bonds, no, skeletal bonds. So there the problem sort of comes. And second thing is, for every CC bond, there will be more number of CH bonds. So statistically also CC bonds are more rarer and buried deep inside than the CH bonds. And so selectivity becomes an issue, proximity to the bond becomes an issue. issue, and because of which CC activation sort of becomes extremely difficult than CH activation. So at least three to two times more number of CH bonds are there than the number of CC bonds in a given organic molecule. And also they are buried deep inside. They are the skeletal bonds. So for metal orbital to reach them, and in the end of the day, if you look at how this activation happens, they are just through orbital interaction of the filled or unfilled valence metal orbitals with the filled and unfilled HOMO and LUMO of the ligand orbitals. Now, if the HOMO and the LUMO are the orbitals which of a particular bond which needs to get activated, if they are very deeply buried in the energy correlation diagram, then the activation of such bonds become difficult. What this question does not make sense. But for CF activation, highest energy is required. That's because the bond is stronger. Let's say what CH bonds are, CF bonds will also be a peripheral bonds like CH bonds, but the CH bond has lesser bond energy than the CF bonds. So the CC bonds will be even more difficult than CF bonds either way. So the question is now you can always compare between CH bonds and CF bond because they are all peripheral bonds. In that case, CF bonds are difficult because of higher bond energy. So that has nothing to do with CC bonds. You're not getting it. CC bonds are the skeletal bonds. CF bonds are the peripheral bonds, similar to CH bonds. If the bond is higher in energy, so obviously it will be difficult to activate it. The CH bonds and CF bonds can be compared, whereas CC bonds are different types of bonds. So it's not fair to compare the challenges of activating a CC bond with that of a CF bond. You got it, no? Do you have any more questions?
So student asks about the final pattern.
What?
Final pattern of
Where?
yeah. There is a sheet they provided for the question. So one student asked about the final pattern of the exam. 50 MCQ, 50 MSQ.
Okay, so there will be 50, all are MCQ and MSQ, 50 each.
50.
1 marks each. How many students are there? Not many, no?
In exam.
Huh? Huh?
And the photo 6.
Hour 2 means?
I am done.
No, exam.
Exam. To this time.
When is the exam?
26 October.
Still that time. See, the bond activations uh, are important process from industrial point of view as well as academic point of view, because through this activation, one can engage in transformation or functionalization of a compound. So it is very important to be able to break down a bond. Now, the thing which catalysis gives is that this allows you to break down a bond in a very selective fashion. And that is the power of organometallic catalysis. So there are specific catalyst and specific conditions in which a certain type of bonds can be selectively cleaved. Now, if all the bonds were to be cleaved simultaneously without any selectivity, then the very tenets of catalysis will fall apart, like it will just implode. So people are more interested in selective functionalization, selective activation, selective transformation of one particular functional group to another, of one particular chemical to another. And from that point of view, selective bond breakage is very important. And catalysis sort of provides homogeneous organometallic catalysis sort of provides a solution to that. Now, not all catalysts can do all type of bond formation. So depending on the electronics and the statics of individual metal center and the electronic and static requirements of each of the substrate, reacting substrate, certain combinations of catalyst substrate allows certain type of bond transformation. And that is then looked at and also optimized to get a very good selective for particular type of bond cleavage transformations. And much of these cleavage transformations, reactions that one observes proceeds through organometallic chemistry and proceeds through covalent orbital overlap in the end. The interaction of a particular bond or a ligand to the metal center using the orbitals, ligand orbitals and the metal orbitals engaging in such interactions, they become all the more very important in predicting and understanding the type of chemical reactivity that they show. These uh, have been discussed, I believe, no? Why compare? So none of them has beta hydrogen. So that is same. So none of them has beta hydrogen. So ideally, according to you, the both will be stable. Now, if you look at the stability means melting point, boiling point, so they also increases with the molecular weights. The higher molecular weights, molecule will have higher boiling point, melting point. In that case, the benzyl, that is the reason benzyl is slightly more stable than methyl. Uh, now, both of them lack beta hydrogen. So both of them are sort of unstable, but relatively between this, because of the higher molecular of the benzyl ligand, they are more stable. Now, if let's say it doesn't mean that let's say all compounds that do not have a beta hydrogen, they will all dissociate at the same temperature. No, and also it does not mean that all compound which has beta hydrogen will also decompose at the same temperature. No, the ones which have beta hydrogen, they will decompose comparatively faster than ones who don't have beta hydrogen. But compounds having several beta hydrogen, several compounds with beta hydrogen does not decompose at a one particular temperature, because just because they have beta hydrogen, they will decompose as per their molecular weight, their inherent stability. And similarly, compounds who doesn't have beta hydrogen, they will also not decompose at the same temperature. They are different compounds. They would have their own inherent stability, and based on that, they will decompose at their own thermal temperature. So these are guided by the thermodynamics as well as the kinetics of those molecule concerned.
Registration 10.
Okay. So let us see how many gives.
So
So about 1/5.
yes.
The negative marking is there?
But MCQ is there. MCQ is there. LSQ not.
Yeah, they should. So there will be negative markings in your exam. So unless you are too certain, I would advise not to attempt. 50 marks negative
50
point.
MCQ, 50 LSQ.
So the negative marking is for half of you. See, whenever you, uh, like, whenever all of you, like, let's say if you take a look, like, read a particular area and you sort of read up on the rules or the definitions or the trends that define a certain observation, please let it be known that there would be a range of compounds, or there will be a range in which the rule will be applicable, and there will be regions where the rule or the windows that the rule will not be applicable. So the more powerful a particular rule is, more fundamentally correct the particular rule is, it will engulf large number of regions, or a longer zone of window. Okay, but there would always be outliers. There would be always be examples which does not conform to the rule, but that does not invalidate the rule. That really does not invalidate the rule, because of the inherent reasons, or why the particular example is an outlier. So, for example, let's say I'll tell you, like, 18 electron rule. Now, it's not like there is no organometallic complexes without EAN rule, or they cannot exist. They exist. There are a lot many complexes which does not follow EAN rule, but that doesn't mean the 18 electron rule is invalid, or the justification for which the 18 electron rule is invalid. For example, one can take up any square planar complexes and of palladium, nickel, or something, and then say that the 18 electron rule is not valid. Because there are so many square planar complexes, but that doesn't weaken the 18 electron rule. So whatever rules that you would follow, uh, uh, they would always be prepared to know that there will be always examples which will not follow the rule. Both MCQs, no, only MSQs, multiple select one, will have negative marking.
MCQ have negative marking.
What?
MCQ have negative marking. MSQ has no
Are you
negative.
sure?
Yes, sir.
So only MCQs, the first half of the
They will mixed up.
only the MCQs will have negative marking. MSQs will not have negative marking.
Whenever you make the question, first 50 is MCQ and the last 50 is MSQ, they say that they will mix up one.
Okay, 50% of the questions will be MCQs, which will have negative marking, and 50% of the question will have MSQs, which will not have negative marking. But it will be mentioned in your question. Which ones will be?
You will understand after seeing the question whether it is MCQ or MSQ.
Yeah, I don't have a model question with me. Do you have any more questions? So again, for people who have joined in late, welcome to this live NPTEL session. We are nearing the end of this NPTEL course, which is transition metal organometallic chemistry from principles to applications. And because of this reason, we have scheduled this live interactive session where we will take up your queries. And then uh, please type in your queries in the in your key in your chat box, and we'll take a look at them in the order in which we received them. Yes, for carbines, I have one doubt. What will be the state of the Fisher carbine? Achha, these are all covered, no? So one will be this is singlet, doublet, and that will be a quadrette and quadrette. Yes. So quadrette will be the stroke one, and the doublet will be the Fisher one. These are explicitly covered, and these and you can work it out also. You can work it out from the orbital model. So basically, if you look at it, it is singlet triplet for the carbene, Fisher being singlet, and the triplet being the stroke, and it is doublet quadrette for the carbines. Even you should be able to draw the correlation diagram, how it is doublet and how it is quadrette for the Fisher and stroke. You should be able to draw it. You should be able to draw it intuitively. You don't need to look at a book because the diagrams are simple to attempt, and also if you can envision a d orbital, if you can envision the orbital of a carbon in its different hybridized state, sp2, sp3, and if you know its valence electron that are involved, then obviously you'll be able to draw the structure, and they're really fun. They're really fun to draw it. You should practice it, and should you take up chemistry in more serious manner, for example, if you want to pursue your doctoral degree or carry out research or go beyond, or even if you want to go and teach somewhere, these ability to this diagram, draw these diagrams would certainly be very helpful. Not only it will enhance your understanding, and also it will be extremely helpful for you. And it's very fun. It's fun to just take a pen and paper and try to draw these orbitals and then look at them. You should always practice drawing. I tell it to all my students as well. That when you look at a picture in a book, you don't get all the details. But when you try to draw them, draw the same picture out of your mind without looking at the book, then you pick up the smaller details which usually we skip or we miss when we look at a picture in front of us. These are MSQ, so probably not much of subjective uh, it, like drawings or questions are being asked, but it's always a good habit to draw chemistry. And drawing is also very powerful in chemistry. If you are to, because a picture speaks 1,000 words. So in chemistry, drawing is something that you cannot avoid. So if you want to describe something, if you want to write about something, first thing, if you just write a chemical equation, that will tell everything. That will take everything. Then if you have to describe a chemical reaction without drawing it. Drawing compounds, drawing chemical equations, drawing orbitals, and looking at the engagement, they are extremely powerful way of communicating your thoughts in chemistry. A good handwriting, a good board work is something which is rare these days, but this is something that one should cultivate. Yeah. It's not difficult. One should cultivate. Nowadays, because of the access to all the gadgets, or because we are tied to gadgets, our handwriting suffers. But that's not something which is a good thing that is happening, because now we are less confident to go up to the board, draw structures, or write sentences in a piece of paper. And that sort of weakens our ability to express ourselves without any AI agent. Bonding is an extremely important area, particularly the area of covalent bonding between metals, between atoms, main group elements, and all. And a proper understanding of that will open up a whole area of reactivity, chemical reactivity of different elements. Which will be easier to understand if one has a thorough knowledge of bonding. Structure and bonding is also a very relevant area in inorganic organometallic chemistry, even in organic chemistry also. So much of the bonding in different compounds we have covered are classical two electron two center two electron bonds, but there is also a large domain of non-classical two electron three centers bond or three center four electron three centered bond. So those bondings are also common, or they have a lot of compounds involving such bonds, and they are quite complicated, but also intellectually very interesting to understand those bonding, and then uh, to understand which will help predict the reactivity of those complexes as well. In this class, have I covered non-classical bonds? No. These are only classical bonds. Yeah. The other codes I do not. Methyl, lithium, and all. Advanced transition chemistry. So I again request you to have any, if you have any queries, please uh, ask now. We still have some time left, and it would be nice if we can discuss some more question in this session. See, I will sort of like go to the discussion on CC bond versus CF or CH. As I said that peripheral bonds, no, CH bonds are more ubiquitous. So there are a large number of CH bonds, and then the CC bonds which are buried deep inside, they are skeletal, so they are difficult. So statistically, skeletal bonds are outnumbered. So probability of a catalyst or metal complex to reach a skeletal bond is very less as compared to reaching a peripheral bond. So that itself is a big challenge for the metal to reach out to the skeletal bonds, just because they are so fewer in number, and there are so many large number of other bonds which they can reach. Now, this is with respect to a particular substrate. Uh, for a particular substrate, skeletal bonds are much difficult to reach or fewer in number than the peripheral bonds. But thing becomes even more complicated if you, let's say, think of the account for the solvent. For example, let's say you are doing a CH bond activation, and you are doing it in a solvent which has a CH bond, let's say benzene and toluene. So the number of CH bond of the toluene, the solvent molecule will be outnumbering the number of CH bond of your substrate molecule. So then for the metal to distinguish between the CH bond of the solvent, which is like maybe 1 million times more number of solvent molecules than to the CH bond of the substrate, that will be even more difficult. And both are peripheral bonds. Okay. So you can understand, or let's say you do it even in chloroforms, let's say CH, there also there is a CH bond, and the solvent CH bonds will outnumber in large extent the substrate CH bonds. So it is really amazing, and that this outnumbering ratio would be 1,000,000 to 1, like that. So it's very amazing how catalyst can selectively get the substrate CH activated, then the and not touch the solvent, or not affect the solvent that way. Uh, so it's not, it's quite challenging. So that's why, they do a lot of optimization and then take a particular solvent for which the substrate activation is optimized, solvent, base, temperature. So optimization conditions also include several experiments, maybe tens of experiments or 50 experiments, just to get a condition in which only the desired activation of the substrate bond, particular bond is optimized or maximized, whereas other activations or other reactions are suppressed. It's really amazing. I request you to ask a few more questions. We have some more time left, uh, so that if you have any doubts or queries, we can discuss them now. So this time only one course is being run,
Yes, sir.
and next semester two
Two.
course. So again, uh, in this live session, like, we request you to ask questions that you may have. This course is nearing its end. So soon you'll have a examination on the lectures which have been aired. And it would be nice if we can go over some of the doubts or queries that you may have before you go for the exam. We have to close at what? 24? Huh?
22 lines.
Do you talk to them? Or 22, 23, something like that. Still time is there. So we have some more time. I request you to send us your queries. We'll wait. This trend also, no, whether it increases or decreases, these trends are different for transition metal versus main group. Uh, uh, Now, there is you will see the opposite trend for the main group than what you observe for transition metal. Now, huh? What? So, uh, uh, now, the overall explanation, then how do you explain two different trends? Uh, how do you explain two different trends, opposing trends, one for transition metal, another for main group? So the idea goes for transition metal, because of the D and the F pore shielding effect of the D and the F orbitals, that the valence orbitals are more tightly held. As a result, the bond dissociation energy slightly increases, I believe. Even though there is if you go down the group, then there is increase in principal quantum number. So you have newer and newer shell added to it. But because of the pore shielding effect of the inner D and the F orbitals, that these electrons are valence electrons are tightly held, and that you get higher bond dissociation energy.
It is not bond dissociation energy. I think he asked about ionization.
He says bond dissociation energy.
Zirconium or titanium, single atom. How the bond dissociation energy?
Huh?
Right.
No, I think he is asked proper.
Ionization.
Not in a compound.
But which
He
type of bond they asked? That
no,
zirconium?
acha, you don't see that ionization energy is of atomic thing, but he asks for the bond dissociation energy. Now, when he says bond dissociation energy, it is implied that he means bond dissociation energy of a zirconium compound. This is zirconium tetrachloride or whatever, any zirconium compound. So there is nothing confusion about the question. Now, for the main group, the opposite trend happens because of the larger principal quantum number, the size is bigger and the overlap integral between the metal orbital and the ligand orbital sort of diminishes. As a result, you get a opposite trend. The main group chemistry, it is opposite. If you go down the trend, and for the transition metal, it is opposite. And that is because related to the presence of the inner F and the d orbitals. Does it satisfy you? So when he says bond dissociation energy, he implies sigma bonded zirconium compounds.
No, I thought that he said bond dissociation energy and maybe single atom zirconium
No,
titanium.
no, that he like zirconium. So zirconium compounds.
complex. I
He
think he
doesn't.
asked about the ionization energy.
No, no. Like it is implied. It is implied that he's asking for. No, no, no. That is not correct. What will be titanium tetrachloride? Total valence electron? Is that 18? No. So when it comes to early transition metal, we follow 18. That is wrong concept. Titanium tetrachloride, tungsten, hexamethyl. So they are 8, 12 valence electrons. So they are not 18. They are not 18. So only if you look at 18, only the mid portion of the transition metal will abide to that. Yes, we understood that you are talking about bond dissociation energy. Not yes, we understood, and the question was answered with respect to bond dissociation energy, not the ionization energy. You may have complexes of early transition metal which are lower than 18, and you have complexes of late transition metal which are also lower than 18. What?
1025.
But the other person didn't show up. Ajay, we are you can still ask a question because we are running on a borrowed time. The live session for another course is about supposed to start at 10:25, but nobody has showed up yet. So we are in borrowed time, but we may have to cut down, stop it as soon as the people for the next live session shows up. But we are still on and कोई आया नहीं है उन लोगों का office से okay then I think we'll have to take your leave. Thank you for attending this live interactive session. You have asked some very good questions and I hope I have answered them to your satisfaction. Please go over the class notes and I wish you all the best for the exam, and I'm extremely happy that a lot of you, about more than 100 students who have enrolled in the course, is going to take the exam. I hope you have gotten something out of the course, particularly that will make you interested about the area, like satisfied your curiosity through the course. Hopefully, some point, if opportunity permits, we may also meet in person. With that, I conclude today. Thank you for attending, and I take you leave. Goodbye. Bye bye. Oh, but only one question the student was asking.